Hello, this is Dr. Bahauddin Abdullah, and this is section 11.3, the integral test. It is not always easy to discover a formula for Sn, and that's why it is not easy to find the limit of Sn to determine whether a series is convergent or divergent. So we need to use different tests to prove that the series is convergent or divergent. The first test we are going to talk about would be the integral test. The integral test says that if you have a function which is continuous, positive, and decreasing, and these are three conditions, on this interval from 1 to infinity, and if the sequence takes its values on the function a(n) equal f of n, then if this integral, the improper integral from 1 to infinity, f of x dx, is convergent, then the series would be convergent. And if the improper integral is divergent, then the series would be divergent. So to prove whether a series is convergent or divergent, you may just use the improper integral from 1 to infinity f of x dx. And we know how to evaluate this in section 7.8. If you find it convergent, then the series would be convergent. But these three conditions must be satisfied. A quick example would be this fact. We remember from section 7.8 that if the integral from 1 to infinity of 1 over x to the power p, this integral is convergent when p is greater than 1, and this is divergent if p is less than or equal to 1. So, using this theorem, this series summation 1 over n to the power p, which is called a p series. So this is called a p series. This series would be convergent when p is greater than 1 and divergent when p is less than or equal to 1. We can use this fact in exercises. So for example, to determine whether this sequence is convergent or divergent, I'll just try to separate this to write it say square root of n over n square plus 4 over n square, subtract the powers, so this is 1 over n to the power 3 over 2, and now this is a p series with p equal to 1.5 greater than 1, so this is convergent p series. And if you take 4 outside, this is also a convergent p series because p is greater than 1. So you can just say that this sequence is convergent because it's sum of two convergent p series because p is greater than 1, and that's it. So this series is convergent. Now there is one important thing to notice. If the integral is convergent, then the series is convergent, but they do not converge to the same number in general. So, for example, if you evaluate this improper integral, you will find it equal to 1, while it's proved that summation 1 over n square is not 1. It is pi square over 6. Both converges, but not to the same number. These are three typical series in which only integral test can be used. So it's better if you memorize them or remember them. Remember that this series converges for p is greater than 1. You have n multiplied by ln n to the power p. Also, if you have ln n in the numerator and n to the power p in the denominator. Also, this series converges when p is greater than 1. This is the third one. You have n ln n times ln n to the power p. Also, this series converges for p greater than 1. So, whenever you ask a question like this, determine whether this series is convergent, you will, if it is one of these three forms, then just check whether p is greater than 1 or not. P here is 3 greater than 1, so this series is convergent. But of course you need to prove it. So let us prove it. And you will prove it using integral test because these series are only proved using integral tests. The only test to use is the integral test for these three series. Okay, so let us take the function f of x equals ln x over x to the power 3. Is this function continuous and positive from 1 to infinity? Yes. It's not continuous for x less than or equal to 0, because 0 is not accepted here and it's not accepted here. So x less than 0, it is x greater than 0, it's continuous, but it's enough from 1 to infinity. And positive also. Okay, let us check whether it's decreasing or not. So let us find the derivative. It's a quotient, so this is x to the power 6, square of this. The derivative of ln x is 1 over x times x cubed, x squared, minus the derivative of this is 3x squared times ln x. That's the quotient rule. Take x squared as a common factor and cancel with x to the power 6, so you will get 1 minus 3 ln x over x to the power 4. Now find the zeros of this to discover where it's less than 0 and greater than 0. So if you find the 0 of the numerator, 1 minus 3 ln x equals 0, take 1 to the other side, divide by 3, raise to the base e. So in fact, x equals e to the power 1 over 3 is the 0 of the numerator. The 0 of the denominator is 0, so it's not important because we'd like to see from 1 to infinity. So 1.4 is 0. Just put a number here, choose a number 2, 3, 4, check whether 1 minus 3 ln x is positive or negative. You will find it negative in this interval, positive in this interval. So the derivative is negative in this interval from e to the power 1 over 3 to infinity. And that's what we need. It doesn't have to be always decreasing. What we need for f prime to be negative, less than 0, ultimately. So f would be decreasing ultimately. I mean, starting from a number to infinity. 10, 100 would be okay. So this is, we can deal from 2. So I will just find the integral from 2 to infinity of this function. If this integral is convergent, then the series from 2 to infinity would be convergent. And of course, the series from 1 to infinity would be also convergent because that's just one term more, which is a number. Now the question, how to find this integral? As I told you, if this is greater than 1, you cannot solve it by substitution. You have to use integration by parts. So let us use integration by parts. If you write it x to the power negative 3 times ln x, take u to be ln x, dv to be x to the power negative 3, use integration by parts, and you will get this answer. So let us take this answer and put it here. So the integral would be limit, it's an improper integral, you replace infinity by t, remember, and take t to infinity. So it's limit t to infinity of this from 2 to t. Now let us replace x by t minus replace x by 2. If you replace x by t, you get negative ln t, 2t squared minus 1 over 4t squared, minus, so this would be plus, ln 2 over 8, 4 times 4 is 16, so you will have this. Now, when t goes to infinity, what is the limit of this term? Well, it's infinity over infinity, so you need to use L'Hopital's rule. Find the derivative, negative 1 over t, the derivative of this is 4t. If you simplify this, t comes down, so it would be negative 1 over 4t squared. Take t to infinity, it would be 1 over infinity, which is 0. So in fact, the limit of this when t goes to infinity is 0 using L'Hopital's rule. The limit of this when t goes to infinity is also 0 because it's 1 over infinity. And the limit of these numbers would be the numbers themselves because there is no t here. So this integral is equal to these numbers. So it is convergent. So the series is convergent. But remember, it's not convergent to these numbers. But it is convergent, and that's what we need to prove. Good luck.